Let's go back to my bed. And my back is hurting a bit. Because I've been sitting on my bed, record this video many days. So I had to lay down and record. Yes, continue.
Was even seen as a self-fulfilling prophecy. 28, 29. The doubling period is often misquoted as 18 months because of a prediction by Moore's colleague, Intel executive David House. In 1975, House noted that Moore's revised law of doubling transistor count every 2 years in turn implied that computer chip performance would roughly double every 18 months. 30. With no increase in power consumption. 31. Moore's law is closely related to MOSFET scaling. 19. As the rapid scaling and miniaturization of MOSFETs. 7. 32. Is the key driving force behind Moore's law. 19. 8. Mathematically, Moore's law predicted that transistor count would double every 2 years due to shrinking transistor dimensions and other improvements. As a consequence of shrinking dimensions, Dennard scaling predicted that power consumption per unit area would remain constant. Combining these effects, David House deduced that computer chip performance would roughly double every 18 months. Also due to Dennard scaling, this increased performance would not be accompanied by increased power, i.e., the energy efficiency of silicon-based computer chips roughly doubles every 18 months. Dennard scale engendered in the 2000 S.20. Kume later showed that a similar rate of efficiency improvement predated silicon chips and Moore's law, for technologies such as vacuum tubes. Microprocessor architects report that since around 2010, semiconductor advancement has slowed industry-wide below the pace predicted by Moore's law. 20. Brian Kotnick, the former CEO of Intel, cited Moore's 1975 revision as a precedent for the current deceleration, which results from technical challenges and is a natural part of the history of Moore's law. 33, 34, 35. The rate of improvement in physical dimensions known as Dennard scaling also ended in the mid-2000s. As a result, much of the semiconductor industry has shifted its focus to the needs of major computing applications rather than semiconductor scaling. 28, 36, 20. Nevertheless, leading semiconductor manufacturers TSMC and Samsung Electronics have claimed to keep pace with Moore's law. 37, 38, 39, 40, 41, 42, with 10 nm and 7 nm nodes in mass production, 37, 38, and 5 nm nodes in risk production as of 2019. 43, 44, Moore's second law. Large early portable computer next to a modern smartphone. An Osborne executive portable computer, from 1982, with a Zilog Z84 MHz CPU, and a 2007 Apple iPhone with a 412 MHz ARM11 CPU. The executive has 100 times Q8, almost 500 times the volume, approximately 10 times the inflation-adjusted cost, and 1/103 wrote the clock frequency of the smartphone. As the cost of computer power to the consumer falls, the cost for producers to fulfill Moore's law follows an opposite trend. R&D manufacturing and test costs have increased steadily with each new generation of chips. Rising manufacturing costs are an important consideration for the sustaining of Moore's law. 45. This led to the formulation of Moore's second law, also called Rock's law, which is that the capital cost of a semiconductor fab also increases exponentially over time. 46, 47. Major enabling factors. A semilog plot of NAND flash design rule dimensions in nanometers against dates of introduction. The downward linear regression indicates an exponential decrease in feature dimensions over time. The trend of MOSFET scaling for NAND flash memory allows the doubling of floating gate MOSFET components manufactured in the same wafer area in less than 18 months. Numerous innovations by scientists and engineers have sustained Moore's law since the beginning of the IC era. Some of the key innovations are listed below, as examples of breakthroughs that have advanced integrated circuit and semiconductor device fabrication technology, allowing transistor counts to grow by more than 7 orders of magnitude in less than 5 decades. Integrated circuit, IC, the raison d'etre for Moore's law. The germanium hybrid IC was invented by Jack Kilby at Texas Instruments in 1958-48. Followed by the invention of the silicon monolithic IC chip by Robert Noyce at Fairchild Semiconductor in 1959-49. Metal oxide semiconductor field effect transistor, MOSFET, invented by Mohammed M. Attallah and Dawan Kang at Bell Labs in 1959-5. It was the first transistor that could be miniaturized and mass-produced. 51. Due to its high scalability. 9. Complementary metal oxide semiconductor, CMOS. The CMOS process was invented by Chitang Sa and Frank Wan Lass at Fairchild Semiconductor in 1963. 52, 53, 54. Dynamic Random Access Memory, DRAM. Bipolar DRAM was developed by Toshiba in 1965, 55, 56. And then Moore's DRAM was independently developed by Robert H. Dennard at IBM in 1967. 57. Moore's DRAM made it possible to fabricate single transistor memory cells on IC chips. Chemically amplified photoresist invented by Hiroshi Ito, C. Grant Wilson and J.M.J. Freechit at IBM circa 1980, 58, 59, 60. Which was 5 to 10 times more sensitive to ultraviolet light. 61. IBM introduced chemically amplified photoresist for DRAM production in the mid-1980s. 62, 63. Deep UV excimer laser photolithography invented by Kanti Jain, 64, at IBM circa 1980. 65, 66, 67. Prior to this, excimer lasers had been mainly used as research devices since their development in the 1970s. 68, 69. From a broader scientific perspective, the invention of excimer laser lithography has been highlighted as one of the major milestones in the 50-year history of the laser. 70, 71. Interconnect innovations of the late 1990s. Including chemical mechanical polishing or chemical mechanical planarization, CMP, trench isolation, and copper interconnects, although not directly a factor in creating smaller transistors, have enabled improved wafer yield, additional layers of metal wires, closer spacing of devices and lower electrical resistance. 72, 73, 74. Computer industry technology roadmaps predicted in 2001 that Moore's law would continue for several generations of semiconductor chips. 75. Recent trends. Animated plots showing electron density and current as gate voltage varies. A simulation of electron density as gate voltage, VG, varies in a nanowire MOSFET. The threshold voltage is around 0.45 V. Nanowire MOSFETs lie toward the end of the ITRS roadmap for scaling devices below 10 nm gate lengths. One of the key challenges of engineering future nanoscaler transistors is the design of gates. As device dimension shrinks, controlling the current flow in the thin channel becomes more difficult. Modern nanoscale transistors typically take the form of multigate MOSFETs, with FinFET being the most common nanoscale transistor. The FinFET has gate dielectric on 3 sides of the channel. In comparison, the gate all-around MOSFET, GAAFET, structure has even better gate control. A gate all-around MOSFET, GAAFET, was first demonstrated in 1988 by a Toshiba research team led by Fujio Maruoka, who demonstrated a vertical nanowire GAAFET which called a surrounding gate transistor, SGT. 7677, Maruoka, best known as the inventor of flash memory, later left Toshiba and founded Unisantis Electronics in 2004 to research surrounding gate technology along with Tohoku University. 78. In 2006, a team of Korean researchers from the Korea Advanced Institute of Science and Technology, KAIST, and the National NanoFab Center developed a 3nm transistor, the world's smallest nanoelectronic device at time, based on FinFET technology. 79. 80. In 2010, researchers at the Tyndall National Institute in Cork, Ireland announced a junctionless transistor. A control gate wrapped around a silicon nanowire can control the passage of electrons without the use of junctions or doping. They claim these may be produced at 10 nanometer scale using existing fabrication techniques. 81. In 2011, researchers at the University of Pittsburgh announced the development of a single electron transistor, 1.5 nanometers in diameter, made out of oxide-based materials. 3 wires converge on a central island that can house 1 or 2 electrons. Electrons tunnel from one wire to another through the island. Conditions on the third wire result in distinct conductive properties, including the ability of the transistor to act as a solid-state memory. 82. Nanowire transistors could spur the creation of microscopic computers. 83, 84, 85. In 2012, a research team at the University of New South Wales announced the development of the first working transistor consisting of a single atom placed precisely in a silicon crystal, not just picked from a large sample of random transistors. 86. Moore's law predicted this milestone to be reached for ICS in the lab by 2020. In 2015, IBM demonstrated 7nm node chips with silicon germanium transistors produced using EUVL. The company believes this transistor density would be 4 times that of current 14nm chips. 87. Samsung and TSMC plan to manufacture 3nm GAAFET nodes by 2021-2022. 88, 89. Note that node names, such as 3nm, have no relation to the physical size of device elements, transistors. A Toshiba research team including T. Imoto, M. Matsui and C. Takubo developed a system block module wafer bonding process for manufacturing 3-dimensional integrated circuit, 3DIC, packages in 2001. 90, 91. In April 2007, Toshiba introduced an 8-layer 3DIC, the 16GB FGM embedded NAND flash memory chip, which was manufactured with 8 stacked 2GB NAND flash chips. 92. In September 2007, Hynix introduced 24-layer 3DIC, a 16GB flash memory chip that was manufactured with 24 stacked NAND flash chips using a wafer bonding process. 93. VNAND, also known as 3D NAND, allows flash memory cells to be stacked vertically using charge trap flash technology originally presented by John Stone in 1967, significantly increasing the number of transistors on a flash memory chip. 3D NAND was first announced by Toshiba in 2007. 94. VNAND was first commercially manufactured by Samsung Electronics in 2013. 95, 96, 97. In 2008, researchers at HP Labs announced a working memristor, a fourth basic passive circuit element whose existence only had been theorized previously. The memristor's unique properties permit the creation of smaller and better performing electronic devices. 98. In 2014, bioengineers at Stanford University developed a circuit modeled on the human brain. 16 neurocore chips simulate 1 million neurons and billions of synaptic connections, claimed to be 9,000 times faster as well as more energy efficient than a typical PC. 99. In 2015, Intel and Micron announced 3DX Point, a non-volatile memory claimed to be significantly faster with similar density compared to NAND. Production scheduled to begin in 2016 was delayed until the second half of 2017. 100, 101, 102. In 2017, Samsung combined its VLAN technology with eUFS 3D IC stacking to produce a 512GB flash memory chip, with 8 stacked 64-layer VLAN dies. 103. In 2019, Samsung produced a 1TB flash chip with 8 stacked 96-layer VLAN dies, along with quad-level SIL, QLC, technology, 4-bit per transistor, 104, 105, equivalent to 2 trillion transistors, the highest transistor count of any IC chip. In 2020, Samsung Electronics plans to produce the 5nm node, using FinFET and EUV technology. 38. In May 2021, IBM announces the creation of the first 2nm computer chip, with parts supposedly being smaller than human DNA. 106. Microprocessor architects report that semiconductor advancement has slowed industry-wide since around 2010, below the pace predicted by Moore's law. 20. Brian Kotnick, the former CEO of Intel, announced our cadence today is closer to 2.5 years than 2. 107. Intel stated in 2015 that improvements in MOSFET devices have slowed, starting at the 22nm feature width around 2012, and continuing at 14nm. 108. The physical limits to transistor scaling have been reached due to source-to-drain leakage, limited gate metalls and limited options for channel material. Other approaches are being investigated, which do not rely on physical scaling. These include the spin state of electron spintronics, tunnel junctions, and advanced seed confinement of channel materials via nanowire geometry. 109. Spin-based logic and memory options are being developed actively in labs. 110, 111. Alternative materials research. The vast majority of current transistors on ICs are composed principally of doped silicon and its alloys. A silicon is fabricated into single nanometer transistors. Short channel effects adversely change desired material properties of silicon as a functional transistor. Below are several non-silicon substitutes in fabrication of small nanometer transistors. One proposed material is indium gallium arsenide, or InGaAs. Compared to their silicon and germanium counterparts, InGaAs transistors are more promising for future high-speed, low-power logic applications. Because of intrinsic characteristics of 3D compound semiconductors, quantum well and tunnel effect transistors based on InGaAs have been proposed as alternatives to more traditional MOSFET designs. In the early 2000s, the atomic layer deposition high film and pitch double patterning processes were invented by Gatish Singh Sandhu at Micron Technology, extending Moore's law for planar CMOS technology to 30nm class and smaller. In 2009, Intel announced the development of 80nm InGaAs quantum well transistors. Quantum well devices contain a material sandwiched between two layers of material with a wider band gap. Despite being double the size of leading pure silicon transistors at the time, The company reported that they performed equally as well while consuming less power. 112. In 2011, researchers at Intel demonstrated 3D Trigate InGaAs transistors with improved leakage characteristics compared